Mr. Chairman, thank you very much for the kind introduction, ladies and gentlemen. I would like to talk about storage, energy, electricity storage, and perhaps a very good starting point now, because so far we heard about the rollout of renewables in Germany, we learned about demand-side management and the challenges in the transport grid. My presentation is structured in three parts. I would like to talk a little bit about the so-called German Energiewende that is well understood all over the world. Meanwhile, that is total reconstruction of our energy system. Then elaborate a little bit on central storage and have a few words on the distributed storage or storage at customer premises. So if we have a look at the plans our federal government has, we see the starting point is at the very left of this graph. We had so far quite a balanced electricity production portfolio. Now, we heard about this, we phase out nuclear up to 2020, and we will have a massive reduction in conventional generation, which is mainly replaced by various kinds of renewables. And then we have an increasing share of imports, and there is still a gap of 25%, which is allocated to decrease in power consumption. I personally have my doubt whether this is all energy efficiency, because maybe counterbalanced by some more electricity due to fuel shift, for example, if we think of heat pumps or the electricity-fueled mobility. So back to electricity. We have the massive rollout, you know about this, which is mainly driven in Germany by wind onshore and the massive buildup of capacity in photovoltaics, which is today, I think, 32 gigawatt installed capacity. Unfortunately, both sources of electricity, wind and solar alike, are, due to their nature, fluctuating. But the time scales are different. Here we have examples. It's a typical curve from photovoltaic production and wind, and we see over one day and over some months that we have massive changes in feed-in. And if we have a closer look at such a typical curve, here we have a day from April 2011, and what we see is three things. That is, we have to supply very high demand. That is, a load here is roughly 20 gigawatt and still increasing. Then we have very, very high variation in load. That is, steep gradients have to be followed. And unfortunately, the third issue is we may have a long period with very low wind speed, which leads to the necessity to supply high load over a very long time. And all solutions which may help in such a situation have to be measured according to their costs, their technical capabilities, and of course their emission profile. And especially in Germany, public acceptance is an issue too. So, and we saw a similar picture today. We have this balance between power generation and consumption to ensure the voltage and frequency level at the wall plug at any time, and there are several technical measures for that. Classical measure is flexible power generation, and all energy supply companies do this and did this for at least 100 years. Then, secondly, we have the expansion of electricity grid, which is quite a cheap measure. And if we imagine we would have a unified electricity market in Europe with a European grid which connects all the countries with strong links, we would be better off than we are today. Then we have the smart technologies. We just heard about flexitricity, which is one demand-side management approach, which is strongly related to the smart grid, because we need a combination of flow of energy and of data, of information, to have better control on the grid itself as well as on the demand side. Last not least, point 4 here is electricity, or here said energy storage, which is the main topic of my presentation today. But keep in mind, we have 4 measures and storage is only one. Take any German newspaper, you will see an article telling you that storage is a silver bullet for all the problems caused by the rollout of renewables, and I think we have a kind of communication hype which is also reflected by public funding. There's a lot of money inside this business. And so we started a study together with Frontier Economics, London-based specialized consulting company with an office in Cologne, and we investigated the situation of storage. Storage may be applied on all levels of the grid. In most countries we have 3 layers. System level, it's 400 kilovolt level, we have the big plants and feed-in, and we may have centralized storage there. Then in the intermediate level, here it is 10 or 30 kilovolt level, we have, for example, smaller wind farms and smaller generators, and have smaller storage units with similar tasks to fulfill. And last, we have the local storage, for example, small battery packs at home in combination with photovoltaics on individual rooftops. So if we have a closer look at all these locations, we see there are major differences in terms of technology, in terms of energy provided, and of the time span which can be covered by the storage. So we see we have the uninterruptible power supply to the very left, and we have, which is most important today, the integration of renewables, which is mainly located in the decentral or on the system level, that is a distribution grid or transport grid. And here we need specific technologies which may help to balance the system in future. And that is the central storage option. And to start, we took the pumped hydro, which is classical and very mature technology. And for the time being, most of system services on this level is provided by pumped hydro in Germany and in most other European countries. However, those technologies are limited due to the geography of the countries, and we may need some option because there is limited potential for new build. If we have a look at the markets this storage is operating in, then we see day ahead, which is most important. We have the intraday, and we have the system services, that is mainly the minute reserve market. Here we calculated what about the economic situation for pumped hydro storage. We assumed a capacity of 100 megawatt over 10 hours time, and what we see is here the revenues are calculated. The absolute figures are not such important today. However, the main message is the main revenues come from the day-ahead market and system improve after 2030. Why? Because we assume that we have a constant rollout of renewables, and at a roughly 50 to 60% electricity production from renewables, we will have an improved situation for the storage because there is more demand to balance the system. And up to a limit of, let's say, 50% renewables, we think, and our calculations support this, we will be have sufficient storage and sufficient balancing power with the existing situation and technologies within the system. Specific to Germany, maybe, but it's discussed in other countries too, is power to gas. The idea is get rid of electricity storage and combine gas grid with electricity grid. And we have the challenge that wind power comes from the north and the load centers with the industry is more to the south. And for public acceptance reasons, we are unable to construct the overhead lines from north to south as rapidly as needed. And so we could get rid of the problem by having wind power put to electrolyzers, producing hydrogen, and transform it to methane, have a feed-in the gas grid, which is capable of storing roughly 200 terawatt hours, which is extremely high value, and then have it in power plants back to electricity again. However, this is quite an immature technology, and a lot of R&D effort is still needed to bring down the cost and to increase the overall efficiency. If we have a more technical look at it, we have the wind power with excess production, and then we go to the electrolysis process and some chemical process called Sabatier process. And after that, we can assume with an efficiency of less than 55% that the CH4, which can be compared to the natural gas, is at a price level of 50 cents. And after the two stages of transporting the gas and having it reconverted to electricity, we would see electricity prices between 50 cents and €1 per kilowatt hour, which is obviously not affordable. And so this technology still needs a lot of R&D to make it more flexible, to bring down the capex and the opex of the scheme. However, if we think of a system with close to 100% renewables, it's the only way out because of the enormous storage capacity. So if we compare the technology options, then we have here the pumped hydro to the very left, then we have the compressed air, which is another technology option. We may have adiabatic compressed air, which is an advanced technology by using the compression heat. We have the power to gas, and only for comparison, we have the lithium-ion battery as an option. And what we see is nearly all technology options are out of the money for the time being and for the decades to come, unless we have massive progress in technology development and we have specific situation, for example, a local grid congestion where we have a very specific situation. That is, for the next 20 years, the existing pumped hydro will be more or less sufficient, and after that, the best candidates are compressed air, and in the very, very long run, it might be power to gas, given the case that learning curves are very steep. So, what should we do? We have the pumped hydro. The compressed air is the next technology option, especially for northern part of Germany, where we, due to geography, can't build any pumped hydro. And we may have the adiabatic compressed air using heat, additionally to the compressed air, and power to gas. And focusing on the action, the recommendation is operate the existing pumped hydro plants and be prepared for some extension in future, maybe up to 5 gigawatt capacity in the long run. Compressed air storage, we don't see any activities. However, we should have more R&D in the adiabatic compressed air because it delivers 70% efficiency compared to roughly 50 with the standard compressed air. And power to gas is up to more and very intense R&D on all stages of this technology process. Summarized, for the system level means there is no need for action in the short term, and let's say with 50-55% of renewables, then new pumped hydro may be economically viable. Compressed air comes in, and power to gas as a last resort measure in the very long term. As I said before, the central storage is only one option. We may have smaller units distributed in the grid or even at customer premises. And we analyze this situation too. And here we imagine a situation, we have a long feeder line with a lot of photovoltaics at the end, and we have an overload situation and wish to get rid of the situation by means of storage. And the option would be simply burying more copper in the ground. And even if we imagine a very long line and all the investments necessary, then there is no case for the battery storage for this kind of application because the storage is quite expensive, still quite expensive. We see that the copper is a simple technology, very low operational cost, and operational lifetime is more than 40 years in comparison to 15 to very optimistic 20 years for a battery pack. That is, in several exemplary cases we investigated, there was no positive business case for any combination of battery with grid. In the medium voltage grid, it's even worse because the specific cost per kilowatt capacity is even lower than in the low voltage part of the grid. So, what about the case battery plus demand at customer premises? Here we have the same, by the way, the same picture we had before on system level in 3 different scenarios we investigated. we have a similar situation, that is, the business case for storage is very critical unless you have very, very specific situation and cost for storage equipment comes down. Batteries are too expensive, and for the large-scale technologies, the downscaling is critical. You can't build very small pumped hydro, and very, very small compressed air is critical too. So back to the low-voltage grid and our customers. You know about our ever-increasing end customer prices, mainly due to the feed-in tariff, due to various taxes and other elements of the electricity price which are not directly related to the energy production. We have at the same time this massive decrease in photovoltaic module prices. In Germany, we currently have offers for a turnkey rooftop installation of PV at a level of roughly 850 to 900 euros per kilowatt peak. And this leads to a situation that we do have the grid parity if we forget about grid fees and all the other cost elements which are necessary to operate the system. And mainstream beliefs in societies there are no concerns about the security of supply, because the generation which is now investing did never experience a kind of real blackout, and so there are no concerns in this direction. Then there is a strong will to be personally independent, to have an energy autarky, and it's the last stage. It's a little bit of get rid of the big energy companies which are seen as a threat, and so small is beautiful and decentralized is good, and this gives a big push for this kind of technologies. And if there is a business case, we for sure would like to participate. So what can we do with the batteries at home? Here we have the typical production and load curve, PV power generation schematic over one day, and we could store the excess production over the midday and recharge the batteries and have the discharging process overnight. Or we may combine this with some demand-side management elements to shift some load over time. And if we apply a battery, here we have a typical case with 4 kilowatt PV combined with 4 kilowatt hour storage. This leads to an increase in the self-consumption of roughly 20%. However, what we have to keep in mind, and this is my last slide, the economics of battery systems depend on avoided power purchases, and thus they do not take into account that the customer still has a grid and still needs the grid for security of supply reasons, and he does not participate in all other system tasks which are necessary to maintain system stability. And thus it's a kind of market distortion which depends on the type of regulation and political will. And this means the business case for storage is very different if you have a macroeconomic point of view or if you look at it from investors' point of view. And so my last conclusion and final remark for today is the business really depends on regulation. That is, be careful if you see a business case, how great is storage? You have to be careful, is it really sustainable in terms of affordable and all the other dimensions of sustainability. Nevertheless, from engineering point of view, it's quite a challenge, and it's a good thing to work on, and so we are happy to participate in this kind of development. Thank you.